All right, everyone, in this lesson we're going to take a look at related rates using trigonometry. Okay, so we'll see how that works. And let's just get right into it with some examples here, okay? One thing to note about trig in calculus is that it's always going to be radians. We never work in degrees here, so just keep that in mind, okay? In the first example, a helicopter is 3,000 feet high and is moving horizontally at a rate of 100 feet per second. It flies directly over a searchlight that rotates so as to always illuminate the helicopter. At how many radians per second is the searchlight rotating when the distance between the helicopter and searchlight is 5,000 feet? All right, let's start with a diagram here, kind of making sense out of what's going on, okay? So we've got our helicopter. Here's mine. There's our helicopter, okay? And it's at 3,000 feet up. So the altitude is 3,000 feet. So I'm going to label this as such, 3,000 feet. Now, it's moving horizontally at a rate of 100 feet per second. So the way I've drawn this, I'm going to have it moving in this direction, okay, at 100 feet per second. It flies directly over a searchlight. Let's call this thing the searchlight, okay? So the shining the light on it. As the helicopter moves to the right, this searchlight's the angle's gonna change so as to always illuminate the helicopter. Okay, so that's kind of what's going on here. So here's how I'm gonna draw this. Basically, you know, there's the starting position of the helicopter. A little while later, it's over here. Okay, and at some point, the distance between the searchlight and the helicopter itself is gonna be 5,000 feet. Okay, so more or less what we've created here is a right triangle. Okay, where it looks like the length of the top of the triangle is going to be getting bigger as the helicopter moves to the right. The fact that it's 3,000 feet high doesn't change. The elevation is always going to be 3,000 feet up and down. Okay, and it looks like the hypotenuse of this triangle will be getting larger as the helicopter moves further and further to the right. Now it says, at how many radians per second is the searchlight rotating? Well, this is our searchlight right here. And at first, when the helicopter's overhead, it's pointing. And what happens as the helicopter travels to the right, this angle is going to increase. I'm going to call this angle theta. We typically use the letter theta to represent angles in this course. Okay? And so basically, we're looking for the rate at which theta is changing. And what rate is that angle changing? Okay? When the helicopter is 5,000 feet from the searchlight. Okay. So, since we're dealing with angles, we should be thinking along the lines of SOHCAHTOA. Okay, this is what's going to bring theta into the problem. When it comes to setting up your initial trig equation, okay, what I like to do, again, let's label the sides here. I'm going to call this side A, I'm going to call this side B, and I'm going to call the hypotenuse side C. Okay? Let's think about what we know. We know that the value of A is 3,000, and that's not changing. So we actually know then the rate of change of side A is 0, okay? The left side is a constant. The length of the side of that triangle is not changing, so dA dt is 0 here. Okay, side B, well, let's see. The helicopter is moving horizontally at a rate of 100 feet per second. Well, side B represents the side of the triangle where the helicopter's flying. We actually know the rate of change of side B here. So dB dt, the rate of change of side B, that's our 100 feet per second. Okay, we know that. And we're looking specifically for the rate of change in the angle when the helicopter and searchlight are 5,000 feet apart. That's going to be exactly when C is 5,000 feet. Okay, so now let's talk about SOHCAHTOA. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. When it comes to setting up your initial trig function to bring theta into the problem, what we do is we look for the sides with a given rate of change and given constant. And we have that here. If you think about it, side A is the side with the given constant. That's side A here. The side with the given rate of change is side B here. We were given the rate of change of side B, okay? So if we come back over to this diagram and I kind of highlight, okay, side A and side B, well, in terms of where angle theta is, we're dealing with adjacent and opposite, okay? B is opposite, A is adjacent. So it looks like we're going to be picking up the tangent function for this problem, okay? So again, we set up the diagram, and we look for, if we're dealing with changes in angles, we look for the sides with the given rate of change and given constant. That's sides A and B here. So since we're dealing with opposite and adjacent, we're going to use the tangent function. So our setup equation is going to look like this. Tangent of angle theta equals opposite B over adjacent A, okay? And I'm actually going to go through taking the derivative of this with you twice, okay? I'm going to show you two ways to do this. First is kind of the longer way, and then the second way I show you is going to be based on the fact that side A is a constant. That's a helpful thing here. But let's go through this kind of the long way first. If we're going to take the derivative both sides now, implicitly with respect to t, on the left we have tan theta, so the derivative of tangent is secant squared, leave the theta alone. Now we multiply by the derivative of theta with respect to time, and just like everything else with respect to time, we're going to get that similar notation back. In this case, it's going to be d theta over dt. If it was an x in there, I would have a dx dt. If it was a y in there, I would have a dy over dt. Okay, but again, this is now what brings that d theta dt into the picture, and that's ultimately what we're looking for. At how many readings per second is the searchlight rotating? We want the rate of change in that angle. Okay, so that's what brings it in here. Now, on the right-hand side, we got to use the quotient rule. Right? So the derivative of the top is going to be dB over dt times the bottom, which is A, minus the derivative of the bottom, dA over dt, times the top, all over bottom squared. And there we have it. There's our quotient rule on the right-hand side. Now, ultimately, we're solving for this. So we got to be able to sub in for dB dt. We know that's 100. We got to sub in for A. We know that's 3,000. We got to sub in for dA. We know that's 0. We have to sub in for B. We still need that value. And we also need the value of secant squared theta on the left-hand side of the equation. So before we can actually go on to solve for d theta, we need to now figure out these things. B is not too bad. Let me redraw this triangle here. Here's side B. We know that side A is going to be 3,000, and we know the hypotenuse is going to be 5,000. So we could certainly use Pythagorean's theorem to solve for that. Actually comes out pretty nice. B is going to be 4,000 on the nose. Okay, so we've got B. We also need the value of secant squared theta. Well, remember, secant theta is the flip of cosine. So if I figure out what cosine is, I can flip that over. Now, we know cosine is what, adjacent over hypotenuse, so that's going to be 3,000 over 5,000, or 3 over 5. So the secant value is going to be 5 over 3, the reciprocal. And so if I square that, we get 25/9. Okay, and so now we have everything we need. So secant squared theta became 25/9. Notice we never actually figured out what theta itself was. We don't need that. Times d theta dt. Okay, dB dt was our 100 feet per second. Value of A is 3,000. dA dt was 0. B was 4,000 over A, 3,000 squared. Okay? And now I'm just going to clean this up. You can certainly use a calculator, but that's 0. That'll cancel with one of those. We get 100 over 3,000, or 1 over 30 on this side. And we'll multiply by the reciprocal, 9/25. And let's see what we get here. So d theta dt is, you can simplify, use a calculator, whatever you want. Let's see, 9/30, simplify like that. So we're getting 3/250ths, and then the units here are going to be radians per unit of time, and I think the unit of time here is in seconds. So the rate of change is 3/250ths radians per second. A pretty small change in that angle, but it's at a significant height. If you were to look up in the air and actually look at a helicopter as it flies by, your neck, the rotation on your neck as you watch it isn't going to be turning all that quickly. Okay? But that's the idea, okay? Now, this is kind of a long way to do that. We had to recognize the use of the quotient rule because we have quotients within our variables. Now, there's a little trick to these that makes life a little bit easier, and that's taking advantage of sides that are given constants. Okay? So in this problem, side A was a constant 3,000 feet. I've said this in previous lessons, but it's a kind of subtle thing. You know, before we start subbing any values in, like 9/25 and 100 for dB dt and all that stuff, you have to take the derivative before subbing in values. I mean, imagine what would happen if I started with this, right? If I just said tan theta equals, instead of b over a, I actually use the values, 4,000 over 3,000 or 4 over 3. I mean, now think about what's going to happen if we take the derivative. Sure, we'll get secant squared theta times d theta dt on this side, but what am I going to get for the derivative of 4/3? I'm going to get 0. There's not going to be any dA over dt, there's not going to be any dB over dt, none of that stuff. We haven't brought in the related rates because we've gotten rid of our variables. So that's why it's important we initially set the equation up using variables, take the derivative using the variables, and then do the subbing in. The exception to that convention is if you have constants. A constant may be subbed into the equation at the beginning. So here's what this is going to look like in this situation. All right, so I'm going back to this. B is changing. Side B is changing, so I'm going to leave that alone. But side A is a constant, 3,000. So I'm going to write it like this, B over 3,000. In fact, I can do a little better than that to make taking the derivative very easy. I could write this as 1 over 3,000 times B. Okay? And it's the same thing as B over 3,000. But now let's take a look at the derivative. On the left, secant squared theta times d theta dt. But on the right, if I take the derivative of 1/3000th of b, I'm simply getting 1/3000th dB dt back. And there's your whole derivative. Notice we had no quotient rule. Notice the letter A doesn't even come into play here. Now we'll go through, we solve for this already. We know that's 25/9. But now look what happens when we sub in this. There's our 100. And again, we're going to get our 1 over 30 here, just like we did up here, and it's going to simplify the same way. And we get the same end result, okay? So you're going to see me do that in future problems now where if we're given a side that's a constant or something that's a constant, that's the one thing we can plug in right away, okay? And it's because its rate of change is 0 that it allows these things to work out the way they do. Let's take a look at the next example. A rocket is rising vertically, so straight up at a rate of 5,400 miles per hour. An observer on the ground is standing 20 miles from the rocket's launch point. How fast in radians per second is the angle of elevation between the ground and the observer's line of sight of the rocket increasing when the rocket is in an elevation of 40 miles? Okay, one thing to notice is that the velocity of the rocket is given in miles per hour, and what we want to know about is how fast in radians per second is the angle changing. So we are going to do a little bit of conversion from hours to seconds here. Okay, we want to make sure that if we're relating something in miles per hours to try and get it to relate it to radians per second, the important thing is that the time units are the same. Okay. Now before I notate anything, I'm going to draw this out. Okay, so here's the rocket. Okay, that thing is rising vertically, so I'll put an arrow here indicating that. Here's the launch point. An observer standing 20 miles away. We'll do that. We can always assume the ground is flat, all right, with these problems. How fast in radians per second is the angle of elevation between the ground and the observer's line of sight of the rockets? That's right here. And our angle would be right here. And now what's going to happen to the angle? Is it increasing or decreasing? As we watch that rocket rise, the angle itself is getting larger. Okay. All right. And at what rate is that angle changing? When the rocket is in an elevation of 40 miles. So at some point that will be 40 miles up. Okay, before again we start notating, let's drop in some variables here. I'm going to stick with A, B, and C for the right triangle. Okay, what do we know? We know a few things. We know A is 20 miles. And does it appear as though that distance is changing? No. So dA dt is 0, which means A is a constant. Okay, so we found our given constant. The rocket is rising vertically at 5,400 miles per hour. That's the rate of change of side B. So the value of dB over dt is 5,400 miles per hour. Okay. How fast in radians per second? So we are looking for, again, the rate of change of angle theta. We'll call that d theta dt. When the rocket is in an elevation of 40, so when B itself is 40. Okay? All right. All right, so given constant was side A, given rate of change was side B, there's our angle. Once again, we're dealing with opposite and adjacent. Once again, we're going to be using the tangent function today. Okay, seems to be a popular one that shows up with these problems. Tan theta equals B over A. I can do that to get started, and I can go ahead and use the quotient rule if I want. Since side A is a constant, though, I can actually plug its value in now and get rid of the quotient rule. Instead of writing it as B over 20, I can write it as 1/20th times B, again, just to get around the quotient rule. Taking the derivative, we'll get secant squared theta times d theta dt. On the right, we get 1/20 times dB over dt. And so to figure out what d theta is, we need to know the value of secant squared. We need to know the value of dB. We know dB, but right now it's in hours. Let's convert to seconds. If it's 5,400 miles per hour, how many miles per second is that going to be? Let's see. So there are what? Miles per hour. There are, we're going to have to, let's see, there are 60 minutes in an hour. And there are 60 seconds in 1 minute. So we got to multiply by 60 times 60 in the denominator. So we're basically going to divide by 3,600 here. Okay. Okay. Hours per minute, minutes per second, right? Just to show you how these things are canceling out here. Okay, so more or less we're taking 5,400 and dividing by 3,600. So dB, 5,400 over 3,600 miles per second. That actually simplifies pretty nicely. That'll be 54 over 36, or 3/2 miles per second. 1.5 miles every second that thing is moving. Okay, so it's cruising. Okay, but again, we've got that. Not a lot of problems require you to do conversions, but just be on the lookout for that stuff here, okay? So anyways, we've got dB. We can sub in here. We need secant squared. So again, we can go the route of cosine if we want. I'm going to show you 2 ways to do the secant squared value. Cosine, well, we need the hypotenuse here. So I could go, all right, well, let's see. 20 squared plus 40 squared equals c squared. 400 plus 1,600. So c squared is 2,000. So radical 2,000 is c. And there's one way to get your answer. There's radical 2,000. Clean it up or don't. That's up to you. Let's see. That would be 100 times 20, which is 10 radical 20, which is 10 radical 4 radical 5, which is 20 radical 5. If we're taking the time to clean this up, okay? So so that's the hypotenuse. So cosine's what? Adjacent over hypotenuse. So that's going to be 20 over 20 radical 5. So the secant value would be the flip of that. And how convenient, that just equals radical 5. And so the secant squared value is just 5, okay? So we get 5 for that here. That required us to figure out the hypotenuse so that we could find the cosine, take its reciprocal, and square it. Well, you may recall a Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. If I actually take this and I divide both sides by cosine squared theta, watch what happens. Here we get 1 sine squared over cosine squared is tangent squared. 1 over cosine squared is secant squared. So what we basically have is what's called an identity for the secant squared function. If I didn't want to bother getting the value of cosine here, if I know what the value of tangent is, I can sub it into this. And what's nice about this problem is that tangent is very easy to come by because they gave us opposite 40, adjacent 20. So if you think about it, we have that very easily. What's 40 over 20? That's 2. What's 1 plus 2 squared? Look at that, same stinking end result. Okay, so again, you know, with the trig stuff, the more you know of this, the easier it might be to come up with some of these values. But let's not lose sight now of the big picture. We're looking to solve and sub in for this. So I'm going to bring this down. Secant squared was 5 times d theta dt equals 1/20th of dB, which we got to be 3/2. So 5 d theta dt equals 3/40ths. Dividing by 5, we get 3/200ths, and again, angles are always radians, and the unit of time here again is in seconds. All right, and so there's the rate of change of that angle. Notice it is a positive value. The angle's getting a little bit bigger, as is the case here. This is the case of the first one too. This angle was getting larger. Notice we indeed got back some positive rate of change. Okay? And let's look at the last example for these. And then you'll see a little bit more trig in the next lesson I go through. We go through some AP problems, okay? So you'll see how some of that shows up as well. But let's do this baseball problem. A baseball diamond is a square with sides 90 feet long. Suppose a baseball player is advancing from second to third base at a rate of 24 feet per second, and an umpire is standing on home plate. Let theta be the angle between the third base line and the line of sight of the umpire to the runner. How fast is theta changing when the runner is 30 feet from third base? So again, how fast is theta changing? We want the value of d theta dt. All right, so let's draw this baseball diamond. It doesn't need to be perfect here. But here's home plate, so here's where the umpire is standing. Here's first base, second base, third base. Okay, sides are 90 feet long. A baseball player is advancing from second to third. So here's my baseball player, okay, advancing in this direction. Okay, and they're running at 24 feet per second. I will notate that in a moment. Let theta be the angle between the third base line, that's this is called the third base line, and the line of sight to the runner. So here's my runner right there. There's the angle in between the two. And what do you notice is happening to the size of the angle as we're watching this third base runner go from second to third? It looks like the size of this angle is going to decrease. So think about what that might mean in terms of d theta here, okay? You shouldn't be surprised by our answer when we get it. So in any event, we've set this up, okay? And look, again, we're really dealing with a right triangle for all intents and purposes here. Here's where the runner's coming in. I'm going to call this side A. Here's side B, which we know is 90 feet. It's the side of the baseball field. And here's our hypotenuse that, again, I'll call C. Now that I've labeled, I have a way of notating. Baseball player is running at a rate of 24 feet per second. So we know what dA dt equals. You may be surprised, though. It's not positive 24 feet. It's actually negative 24 feet per second. And why do you suppose that's the case here? What's actually happening to the length of side A as this runner advances? It's getting shorter. So because the length of the side is decreasing, we have a negative rate of change, believe it or not. We know the value of B is 90. And we actually know that that's a constant. This side of the triangle is not changing. So dB dt is 0. So this time side A is the given rate of change, side B is the given constant, and we're looking for d theta dt when the runner is 30 feet from third base. So that's going to be that length right there. A itself will equal 30 feet. Okay, so again, go slow, rewind this a little bit if you need to get this down. It does take a bit of practice before you get really, really good at this stuff, in my opinion, okay? But again, kind of going with the convention of earlier. Here's my angle, I've got opposite, and I've got adjacent, so today it's all about the tangent function. Tangent of theta equals opposite A, that's changing, I'll use A, over B, but that's a constant, so I'll use the 90. And again, I can write this as tan theta is 1/90th of A. Taking the derivative, secant squared theta times d theta dt equals 1 over 90 times dA over dt. If we have secant squared and we have dA, we can solve. We do have dA. That's negative 24. And I'm going to use my identity just to reinforce it, because I can get the tangent value pretty easily here. Tangent is going to be 30 over 90 at this moment in time. And I'll clean that up a little bit. And it looks like we're going to get 10/9 for our secant squared value. Okay, presuming I did that correctly. Okay, so let's see, 10/9 of our rate of change in the angle is equal to negative 24/90. Let's multiply by 9/10. And simplify. We're looking at negative 24/100 radians per second. And again, you can simplify that if you want to, but not the most important thing. Notice that d theta dt, the rate of change in the angle, came back negative, as we would have expected it to, since the size of the angle is getting smaller. Okay? You should be able to try a couple of the homework assignments now with this, and we'll have one more lesson to go. But as always, if you have questions, particularly as things get trickier, reach out, okay? Have a great day, everybody.